Okay, so let's talk about the quotient ring construction. We already saw the quotient group construction in group theory, and this is analogous. So recall, if F from R to S is a ring homomorphism, then kernel of F, which means all the elements of R that map to 0 when you apply F, is a two-sided ideal in R. So this means, if we call this thing I, i.e. I is a subring of R, and furthermore, it has a stronger closure property. If you take an element of I and any element of the ring whatsoever, then the product of these two things in either order and the other order as well. And the product of these two things in either order belong to I again. So kernels of homomorphisms are two-sided ideals. Conversely, we'll see that any two-sided ideal in a ring appears as kernel of a canonical homomorphism. You say, which homomorphism? It's the canonical homomorphism onto the quotient ring, called the quotient homomorphism. So this is exactly what happened when you have a normal subgroup in a group. So here's the setup now. Let R be a ring. Let I be a two-sided ideal. This means two-sided ideal. And I want to construct a new ring called R mod I and a surjective ring homomorphism from R to R mod I called the quotient homomorphism. Want. From group theory, we already have quite a bit of this. You see, R is after all an abelian group under plus. Let's write something down. From group theory, we have quite a lot. R plus 0 is an abelian group, and I is a subgroup. Of course, it's abelian. Oh, of course, it's normal. It's a normal subgroup of R plus 0 because R plus 0 is abelian. Every subgroup is normal. So R mod I makes sense as a quotient group. This is the set of cosets like this, A plus I, A in R. That's what the quotient group meant. That does make sense as a additive abelian group. Is an abelian group. With identities 0 plus y and addition defined such that when you add a coset A plus I to another coset B plus I, you get the coset of A plus B. And this is for all A, B in R, right? Also from group theory, have a surjective group homomorphism pi from this abelian group to the abelian group R mod I, given by pi of an element is the coset of that element for all A in R, and the kernel of this homomorphism. Notice the kernel means exactly the same thing whether you're thinking of this as a group or as a ring. It's all the things that map to the zero element, which is the identity element of S as a group, abelian group. The kernel of pi is just I. Right. So all this you have. So what is extra? What do we need to do here extra? It is we have to show that this R mod I actually has a multiplication as well, so that you can make it into a ring. And this map pi is actually a ring homomorphism. So that amounts to making this claim. Let's write down a claim. There exists actually a unique ring structure, but I don't want to check that right now. A ring structure on R mod I such that this map pi, which is right now a group homomorphism, actually becomes a surjective ring homomorphism. Becomes a surjective ring homomorphism. So what do you want? That amounts to, if you give me a A and a B in R, then I want pi of A times pi of B to be pi of AB. And I already know what pi is. So this means A plus I times B plus I has to be AB plus I. So the coset of A times the coset of B has to be the coset of AB. Except one has to check that this is well defined. What do I mean? I mean, if you give me a coset C and a coset D, a coset can have multiple representatives. You could choose a representative little a and another representative A prime. Here you could choose a representative B, you could choose a representative B prime. And you can choose any element in this coset, and then this coset is A plus I, but it's also A prime plus I. And similarly for D. So to make sure that the right hand side gives you the same thing. Right? And that would be the content of this next lemma. It says let C and D be two cosets in R mod I. Choose two elements from capital C, call them little c and little c prime, and choose two elements from capital D, call them little d and little d prime. Then the coset of CD and the coset of C prime D prime are the same.